So in this example, we're going to look at rotating a figure about the line y equals -1. So instead of rotating it about either the x or the y axis, we're going to rotate it about this line down here. And there are a few complexities in this problem, but I think it's a good problem to look at. In this case, we're rotating the region enclosed by the graph of y equals x to the 1/3. That's going to be this curve, and it actually extends this way, but I didn't want to make the picture too messy. X equals 0, that's the y-axis, and y equals 1, that's the bound up here. So my first step is to sketch a picture of this and to decide what my shells are going to look like. So because I'm rotating this around the line y equals 1, I need to be careful about maintaining the radius, that this lower point is going to circle around the line y equals -1. This point right here is also going to circle around the line y equals -1, so it's going to intersect down here. And my region, this point is also going to circle around y equals -1. And my region down here is an exact mirror of that region up there. So this shape is actually similar to the shape that we saw before. It's going to enclose this whole base, sort of a dotted, that's the base. So it's going to be sort of a hollow parabolic bowl tilted on its side, although it's not a parabola per se because of the cubic nature of the function. Phew! Let's find the volume of this using shells. Notice that in this case, it doesn't make sense to have shells that go sort of widthwise, that my shells are going to have to be shells that look like this. And how do I decide what my shells look like? It depends upon how you're rotating around an axis. So this is my picture of what one of my shells is going to look like. Right? Maybe that's a hard picture to be able to visualize. I tried to do it in red so you could see sort of the coloration of it. But in general, if I'm rotating something about a vertical line, it means my shells are going to have dx's. Anytime I rotate about a horizontal line, it means my shells are going to have dy as their widths. Maybe I can even write that down. Rotation about a horizontal line yields shell widths of delta x. Oh wait, horizontal line, my shell widths are delta y. I'm looking at this picture in this particular case. My shell widths are delta y because I'm taking this as my width. This is my delta y. And the only way that I can tell actually is by drawing a picture. I don't memorize this as a set of rules. Another thing that's important to note is that this is exactly the opposite of what we did with discs. If I was thinking of splitting this up as sort of slicing bread, then my discs would have been of delta x width. But now that I've identified that it's a delta y, the pieces aren't as hard as you think that it might be. Let's go ahead and find out what each of the pieces for one shell are going to look like. So if I'm looking at one shell, I want to know what is the height of each of these shells. The heights of the shells are going to extend from the line y equals, or x equals 0, out until it hits this curve. So it means that my heights are going to go from, in green, from here to here. And I know an equation for that curve. The equation for the curve is the equation, let's see, I'm looking at height. It's going to go from 0 to y equals x to the 1/3. The problem is, what is this width? This width is my x-coordinate, right? The height goes from 0 out into whatever my x-coordinate is. And I don't have this function written in terms of my x-coordinate. So I need to rewrite this function to be able to solve for x. If I hadn't, well, yeah, let's go ahead and just rewrite this and solve for x. If y is equal to x to the 1/3, this is something that's easy to do in my head. I can cube both sides. Cubing is a 1-to-1 function, and I'm left with y cubed is equal to x. So my height in this case is y cubed. Let's look at that's the height. What's the radius in this case? The radius of any given shell is going to start from the center point, from the point of rotation, and extend out to be the y value height. So you would want the height to just be the y value, and it's going to be 1 bigger than the y value. It's 1 bigger than the y value because we're rotated around this line, y equals -1. So the radius in this case is going to be the y coordinate, y, plus 1, because we're rotating around this line that's 1 further away. I'm measuring the radius of this shell is in green. And then the final thing that we already found, we know that this is going to be a width of delta y. And maybe while I'm here, I have to think about where do my delta y's start and where do my delta y's stop. I want to think what is the center of this figure and what is the very outside edge of this figure. And in this case, we have to be a little careful. Although we're rotating around the line y equals -1, that's not where my figure starts, because my figure is sort of empty right there. That's the hollow cylinder in the center. That my figure doesn't start until I hit y equals 0, and then it extends up until y equals 1. So that means that my bounds go from y equals 0 to y equals 1, because this is the innermost part of my figure and that's the outermost part of my figure. With all of that information on this challenging example, we have enough to be able to set up the integral. Recall that my integral should be the integral of for one particular shell, it's going to be the circumference of that shell, which is 2 pi r, times the height of each shell, which is h. And in this case, my integral is with respect to y, dy. My y values in this particular case are going from 0 to 1, 2 pi r. And we already found, maybe I should put this down here so you can see the pieces. We already found what the radius is. The radius is going to be y plus 1. That's my radius. And the height in this case, we already found what our height is going to be. Our height is going to be y cubed. Looking back on this picture, if I had used a height value of just x, because it's just how far over it is on this function, that wouldn't make sense. You can't have x's in here because we're integrating with respect to y. So no matter what happens, I need to make sure I get rid of all of these variables, these r variables, these h variables, whatever variables I have to integrate with respect to y, so I need to convert them into functions of y. But now that we've done all of that hard work, the integration is actually the easy part. I see that I have a constant of 2 pi that I can pull out front. Integrating from 0 to 1, I'm going to do the distributive property. This becomes y to the 4th plus y cubed dy. Let's go ahead and integrate. I get 1/5 y to the 5th plus 1/4 y to the 4th, evaluated as y goes from 0 to 1. Plugging in my upper bound, I get 2 pi times 1/5 plus 1/4. Subtracting out my lower bound, I get 2 pi times 0. If I plug 0 in, I get 0 each of those times. A fifth plus a fourth is 4/20 plus 5/20 is 9/20. 2 times 9/20 is 18/20 pi, which is the same thing as 9/10 pi.